Yeah, so here's Tom to tell us how to make over code.
Yeah, I'm one of the software managers, and I've been writing code for longer than I care to say.
I got you, Beach.
Old Fortran days. I'm sure Heidi remembers those well. So let me share my screen.
I thought it was cool the other day. You alluded to paw.
I did.
Yeah,
you remember?
I got excited for you. Man, I was a Kumak master.
Oh man, back when Yoda was Yoda. Okay, let me use my. I'm going to turn my video off and use my big screen here. Okay, so let's go ahead and get started. I've got a session set up on my own desktop here. I'm going to SSH into GPVM and show you some of the tools. But first, I'm going to talk about, let's see, can I hide this video panel? Come on, hide that. Okay, but first I want to talk about general advice for optimizing your code and compilers. So I guess I've been doing or looking over the surveys of what people have been doing on the collaboration. And some people use C++, but there's a growing community using Python. And Python, actually, a lot of the tools call C++ libraries underneath, and the user interface that's exposed is a non-compiled interpreted scripting language, which is Python. So we're going to talk about C++ because that's what a lot of the framework code is written in. And when people talk about using tens of millions of hours of CPU in order to simulate and reconstruct fire detector, proto-DUNE data, the near detector software efforts are coming along, but they haven't grown to the scale of the fire detector. So a lot of the big applications are written in C++. And this is a compiled language, which means that the compiler actually does a lot of this optimization for you. So if you want to write efficient code, often you can write any code and the compiler will go and make it more efficient for you. But it is very easy to write inefficient code that even the best compiler cannot rescue. So we'll talk about some of the things that you can do to tune up your code to make it better. Of course, there are a lot of reasons to make code run faster or use less I/O or less memory. And that is because you, as a physicist, are usually in a hurry. You want to get your results out quickly. For the conference, you want to graduate, get your PhD. You don't want to be sitting around waiting for your grid jobs to run. So the other reason is because we share our computers, and most of the computers we run on, we don't own, meaning that we have to give them back when we're done with them, which means that if we're done quicker, people are happier with us, especially your collaborators. So if your collaborators are waiting to get their jobs through and you're busy taking all the computer resources, they will get mad at you because they want to do their stuff too. Okay, so what are the simplest things that you can do? Well, certainly using the prof build, which is one of the qualifiers on setting up DUNE software, will help your jobs run faster. So we build two kinds of software stacks. One's debug and one's prof, and these names are historical. Prof really means compiled with the optimization flag turned on. I believe it's 03, and debug means compiled with optimization turned off. We'll later in the code, how to modify module section, I'll talk about actually debugging an art job, and I've got some examples for debugging some code today. We should get to that. Both the debug and the prof builds are built with debug symbols, so they're both debuggable. But the prof one is harder to debug because the compiler will often rearrange the execution order, and the program counter will bounce around while you're stepping through your program. It'll go to the top and the bottom and execute a few lines in the middle and then go back again. And it's hard to tell just how much of which lines are executed at a time. And some memory is not very easily queryable with the prof build. Nonetheless, the prof builds are at least 4 times as fast, sometimes faster than the debug build, just because it takes advantage of things that work faster on the CPUs that we have when you run the optimizer. So please almost always run prof, even when you're debugging, and you might try to get used to debugging the prof optimized code, unless you really have a struggle trying to understand what the debugger is telling you. And then you can revert to the debug. Compile your interactive root scripts. So if you just .l myprogram.c++ instead of .ling myprogram.c, it'll compile it. If you put only 1+ after the C, it will compile it only if necessary. So if you keep on rerunning it and not changing it, and just rerunning it on new data sets, it won't recompile if you just have the 1+. So this is the root C interpreter, by the way, is super duper slow. And it used to not even be all that C++ compliant. These days, however, it uses Clang underneath, so it is a much better match to the actual C++ language. You might be surprised at what's slow in your program. So some things that don't look inefficient really are, and some things that look inefficient might actually not be so bad. So get some data, and the data that I've collected, and I've got a few examples that we'll get to, is using Valgrind. And the Valgrind documentation actually tells us to pronounce it Valgrind, but no one ever says Valgrind in my experience, so I'll call it Valgrind. The Valgrind manual is actually a lot of fun to read, and it tells you how to pronounce it, and it's full of amusing anecdotes. So gprof is another profiler that is easy to find. I've been using the callgrind from Valgrind because that works out of the box with an art job. And the debugger can also be used as a simple profiler. So if you want to know what's slow about your program, if your program is really, really, really slow, and this is true even for big programs. Big programs, of course, are harder to diagnose to see what's slow about them because there's so many places in them that could be slow. But if your program normally runs fast, but every now and then hits a really slow event, or it used to be fast, but now it's slow, then often it's just one place that's slow. So if you've got a program where I've got 100 slow operations in it, then it's hard to whack all the nulls. But if you've got one huge dominant slow spot, then the debugger can be the easiest way just to track it down. So you start your program in the debugger, and then you wait until it starts doing its slow thing, which maybe you don't have to wait at all, because it always starts doing its slow thing. Although the initialization phase of an art job can sometimes be slow or take a little while. But once you get it going, then you just push the pause button, and then you see what it's doing. And 99 times out of 100, it'll be doing the thing that's really slow. And then you just figure out what it's doing. You might want to look at the loop counter and see that what it's looping over. Is it looping over billions of things when it really only has to loop over hundreds of things, for instance? And then you can see by stepping through the program what it's doing while it's taking its time. And that's often the thing that I resort to first. Even if I don't think that my program has bugs, I'll still run it in the debugger just to see what it's doing and make sure I understand its actions. Onto coding. You shouldn't perform calculations or do I/O that will be ignored. And this is more common than it seems. And one of the reasons for this is that people write code in order to perform a particular operation, and then they'll change their mind, or they're doing systematic uncertainties, or they decide that they only want to rerun part of an analysis because they already have the results from the rest of it. So what they'll do is they'll rerun the entire job because the job does everything, and then they'll ignore most of it and then pluck out only the little bit that corresponds to the systematic uncertainty that they're calculating. So that's okay if the overhead of doing that is small, but if you're using millions of CPU hours to redo the entire analysis when you only have to evaluate one systematic, maybe you should invest some time in commenting out or switching off the things that you don't actually need. So one example of redoing calculations and needlessly is to put things in loops that don't need to be in loops. So here's an example with some bad code here, is that if I want to sum up a bunch of vector entries and divide them all by the square root of 2. So this loop will take each element out of this vector and divide it by the square root of 2 and sum them all up. Now what's bad about this is that it calculates the square root of 2 over and over and over again. And square root is a little bit on the slow side. And also the divide is not the fastest. Turns out that multiplies, even on modern CPUs, have a lot less latency than the divides. I think the average time may be one clock tick for a floating point operation, but there's more hang time in the pipelines for a divide. And you can look up instruction timing on the web to see how various processors compare when they are multiplying and dividing. So here's the faster code, is that you lift the calculation of the square root of 2 out of the loop, so you don't do it n channels times, store the result in a double precision number, and also store the reciprocal of it. Instead of doing the divide, you do a multiply. So this will speed up because there are a lot of square roots and divides that are just removed and replaced with a much faster single multiply. Okay, another example that's really bad and easy to avoid is not using power or POW in order to evaluate square roots. So I've seen this a lot in code, is that people will square something by taking the second power of it, and then they'll take the square root by using power of 0.5. And the problem with the power function, which calls the C math library POW, is that it is a several step process. It takes the logarithm of the first argument, multiplies that by the second argument, and re-exponentiates it. So this is a 3-step operation that really needs to be only 1 step if you're doing, say, square root. And a multiply is even faster than power of 2. Now, some math libraries may be smart enough to tell that the power is 2 and turn that into a multiply, but not all can be guaranteed to be that smart. You may also find that compilers may even be smart enough to detect that you're doing this constant calculation over and over again and lift that calculation out of the loop as part of the optimization procedure. But do not count on it. And I think we've even found in the upper case that even the optimization turn on in GCC was unable to discover something like that. And we had to do it ourselves. Okay, another issue is that if you decide to use multiply instead of square or power, that's a good thing because that reduces the log, multiply, exponentiate, and just turns it into a single multiply. But if you're squaring a slow function, so here's a bad example. Suppose I need to calculate the value of a slow function that returns something that I'll call x. And if I call that function twice, that's violating my first rule above by calculating things that I'm just going to throw away later. So what I really should do is calculate the slow function once and then multiply the result by itself rather than calling the slow function twice. And the slow function might do file IO. You might need to call the slow function twice if it prints something to the screen and you expect it to print something twice. If it has side effects, it might write something to the file, but if it just reads a file or does something horribly slow in calculation, please just call it once and then square the answer. So that's what tmath square does. You might wonder why the root authors provided a function that just multiplies its argument by itself. Why don't we just do that in the code ourselves? And the reason for that is so that you don't have to call the argument twice. So if that argument is a function, this just lets you wrap it around that without declaring a new variable and then multiplying it by itself, because the new variable's buried inside the tmass square function. Another trick is that if you don't have to square or square root things, don't. So if you're calculating a bunch of distances and you want to place a cut on the distance, you can calculate the distance by squaring the components and then taking the square root of the sum of the squares and then comparing that with your distance cut. Well, square root can be slow, so let's not square it. Let's take the square root. Let's just compare the square of the distance against the square of the cut instead. So that removes one of the square root calls. And square root is surprisingly slow. I think the library function actually has to check to see if the argument is not negative. And the square root instruction itself is a lot slower than a multiply or divide or an add. I remember back in the old days when we were using VAXes, I think square root was 10 to 100 times slower than a multiply. So another trick is that if you are looking through a big array for something in particular, and you've got some criterion that you want to find an item in an array, maybe you're applying a cut, you want to find space points that are close to a desired location. So it's not actually comparing the value. You might actually have to compute a distance and pick out the element of a vector that satisfies the first element that satisfies some criteria. So here's a loop that will loop over a vector and see which one is the first one to actually this finds the last one. So because it loops over the entire vector, and if it finds one, then it sets this index found to be the place where it found the desired value, set the flag to be true, and then keeps on looping. So even if it finds what it wants, it still keeps on looking. So that's kind of dumb. You can speed this up by saying, well, if I only want to find the first one, I can put a break statement right here after found. If I write the word break here, it'll stop this loop and bail out and leave you with the first one. So this one leaves the last one if that's what you want. If you really wanted the last one, you should step through the loop backwards instead of forwards and bail out of the loop when you find the first one. Now, one of the issues here is that if you are looking for, say, how many elements of your vector are less than a particular value, it's good to sort that vector, especially if you have to search through it multiple times. So instead of a vector, you can use a standard map. And when you put things in the standard map, they get sorted. Standard unordered map is not a sorted map. So if you really need the sorting feature, you can go ahead and use the standard map. But standard unordered map is a bit quicker because it uses hash tables for looking things up. And the hash table has order 1 execution time, meaning that no matter how big the map is, the actual lookup time for items in the map does not grow with the size of the map. Looking things up in a standard map, not the unordered standard map, is order log n, because you have to, what it does is it sorts the keys on input. When you push things into the map, they go in sorted, and then looking through a sorted list by doing a binary selection, you say, I'm going to check the element in the middle and say, is it bigger or is it less? Then I'm going to check, if it's less, I'm going to check the element midway through the bottom half or the top half if it's bigger, and then keep on binary chopping. So you get this log of 2 scaling for looking for things in the standard map. So if you're looking for things just by looping over a vector, it's a lot easier to find things if they're sorted than if they're unsorted, especially if you have to look through it many, many times. So if you've got a sorted vector, you can use standard upper bound And there are examples of using upper bound and lower bound, which do the binary search through a sorted array, which is much faster than just looping through the array and checking each one. Okay, I found that was actually one place where we were using 10 minutes of CPU per event in the backtracker. Several years ago, people were storing hits and space points and just looping through arrays, trying to find which hit was going with which space point, and just sorting it and doing the search on the sorted array was so much, a sorted vector was so much faster. Another little small optimization that you can do is to make sure that your math consistently uses the same precision in all the components of an expression. So if you've got floating point numbers, floats, and doubles, and a mixture thereof, your compiled program has to convert between floats and doubles in order to calculate an expression. And usually it upconverts things to the maximum precision that is consistent with all the elements in an expression. So here's something where we're adding up a bunch of, we're calculating a double precision number here and then putting the result in a float, and then we're putting the float, adding the float back into a double. So there are two conversions here. We do this double precision calculation, stuff the answer in a float, and then add that float back to a double. And those involve a couple extra conversions, which are slow. And here's a complete double precision version of that. TMath square, by the way, is a template function, so that it'll do this calculation, which is just to multiply in whatever precision the input variable is. This, by the way, I'm not sure if I have a item on this page, but there was something that tripped us up a few years back with some root code. And that was that there was a method in TMath that calculated the RMS of a vector of input variables. And the problem with it, and I think it's been fixed, it was a bug at the time, but it's, even though the root code is now not buggy, your code, you might want to know about this bug because it's easy to make. So the problem is that the root code that did the RMS, here's a square function, but imagine that we have an RMS of an array as a root function. The calculation in the root code, which was doing a sum of squares to calculate the root mean square, was done in the same precision as the input variable. So this is okay if your input is a vector of doubles, because then all of the calculations get done in double precision. If you're calculating the RMS of a very long vector of shorts, and shorts are 16-bit integers, then it's very easy to overflow the sum of squares if the sum of squares is a short. So the root code now calculates the sum of squares as a double precision. If you pass a big long vector of shorts to the root RMS calculator, it's going to calculate a whole bunch of conversions of shorts to doubles and be a little slow, but at least it'll protect itself from overflows. So sometimes you want to mix precision, especially if the shorts came from the data acquisition system, you don't have any choice, but you still want to calculate the RMS of it. So even though these bad examples are shown as something that's a little slow, sometimes you have no choice but to convert a whole bunch of integers to floats or integers to doubles and then doing the calculations. Another thing I noticed years ago is that if you have NANS or infs, NAN means not a number. If you take the logarithm of a negative number, or you get a NAN. If you divide by 0, you get an inf. So these are special numbers that are not valid in floating point calculations. And back in the really bad old days of Fortran, and I think you can still turn the switch on in C++, is that your program would crash. Old Fortran programs, you take a logarithm of a negative number and the program crashes. And then you go have to debug it. And that was good because no one likes invalid results. But the standard behavior of C++ and C programs, if you have inputs that are out of the domain of mathematical functions, they'll just chug along, and the result will be a NAN. And then the NAN plus a NAN, or NAN times a NAN, or the square root of a NAN will be a NAN. And your program will continue. The problem here is that you may not, well, the reason why this choice was made is that you may not care. So a lot of programs will calculate results that will eventually be thrown away, or they're just diagnostics, and they may be for edge cases that you don't care about or know about, and say you want the RMS of a vector with no entries in it. And that's okay that it doesn't have a value because you're not going to use it anyway for the cases where your vector has no entries. However, NANs take longer to process for reasons I don't understand. A lot of math functions check for NAN and then do something else, or maybe throw an internal exception and go through some extra processing code. So the floating point units may have to do extra work when you give them a NAN on modern CPUs. So check your results for NAN, or check the domains whenever you take the square root or logarithm or divide by anything in your code, so that you don't get results that you don't expect. And that's a good thing anyway to do, because often that means that there's something wrong with your calculation or your numbers. Another thing you can do to speed things up and save some memory is to pass objects by reference, especially the big ones. So when you pass an argument to a method, like this at method for a vector, here's I, you pass it in I, that's passed by value in C and C++. Unless it's otherwise specified, everything gets passed by value. That means that a copy of the input argument is pushed on the stack, and then the method is called. So if the object is big, like it's a giant vector, you don't want to copy a huge vector onto the stack. One of the reasons why objects are passed by value in C is so that it's clear that you can't modify them. So if the standard C way of doing things is, if you want a C method to modify its argument, you have to pass in a pointer to the thing that you want to modify. C++, however, works a lot like old Fortran, where the called method can modify the values of its arguments, because the pointers are essentially passed in implicitly because you pass things by reference. So what C++ lets you do is declare methods where the arguments are references, and then the caller, it's not clear when you call a method with an argument, whether that's passed by value or reference. You actually have to look at the declaration of the method to see whether it's passed by value or reference. But if it's a vector, a big vector, you'll save memory and CPU in order to, if you pass them by reference, but it also means that the called method can modify the arguments. You can also use references to catch the returned objects created by methods. So if a method produces a vector, for instance, then it's a good idea not to say that the output of the method gets copied into a separate variable. Instead, it's good to use a reference to catch that. And there's some actual live code from the channel map for the vertical drift cold box, where I initially did something stupid. This is the bad code example from me. And Alessandro Thea corrected me and said, or gave me a good suggestion, say that what the problem with this bad code is that the channel map was a unordered map of unordered map of unordered maps. So the idea was there's a warm interface board, a WIB, there's the connector, and then there's the channel ID. And we wanted to look up offline channel as a function of these three input keys. So if you just have one map, you only get one key. But if you have a map of maps, you can map them from each key. So the idea was that I would find use the first key, check to see if it was in the map, and if it's not, return a guard value, and then look up the WIB connector and the cold electronics channel. And the stupid thing that I was doing was that looking up this map value from, say, the first one, I was copying the entire map into this M1 variable. So this map of maps undid the first lookup on the first thing, but it copied the entire contents of that second of that map into M1. And then I would look up things in M1 and copy the contents of that map into M2, and then look up that. So that was massively stupid. And it was the entire channel map. And it wasn't so big because it was the vertical drift cold box. It only had 1,000 channels in it, but the FAR detector is going to have 300,000 channels or more per module. So the idea here was to look up things in the map, but then use a reference to catch the result. So this doesn't copy the map. Is that a question? Everyone's groaning at my stupid code.
No, someone forgot to
I think
mute.
someone needs to mute. I'm trying to see if I can mute them, but I can't seem to figure out how to do it.
Might be under participants.
Yeah, I'm on
It's okay.
participants.
Thank you, Dave. It's okay.
Yeah, I think we're good. Okay, so the only difference between the left-hand code here and the right-hand code are these little ampersands. And the reason that I use auto here is because this type is really disgusting. It's a standard unordered map of unordered maps of unordered maps, and I would have to type all that out. But instead, C++ lets you automatically determine the type. And that's easier if the underlying type changes, then you don't have to rewrite code to put in the explicit type here. I find it a little bit confusing to read code with a bunch of autos in it because then I don't know what the type of anything is. So for instance, I don't know if second is meaningful just by looking at this. I actually have to read the header file to see how this info to channel map was defined in order to see if any of this stuff makes sense or what these objects are. But it's convenient to use. So the other comment that I have here is that the suggestion that I actually got from Alessandro is that maybe I should just use the map lookups with the square brackets and then just index the map with square bracket map lookups with square brackets instead of using the find method and then comparing the to see whether the object was found in the map or not. And I went and used this rather uglier solution where I would check to see if something was in the map and then return the guard value. Alessandro proposed just using the square bracket lookup of map and then catching the exception that would be thrown if something wasn't in the map. And this violates one of my little rules, and that is to avoid using exceptions that are caught as part of normal program operation. So if there are channels that are not in the map, and it turns out that the vertical drift cold box has some features to it because they were using old proto-DUNE front-end motherboards, which had 128 channels in them, but the cold box did not have a multiple of 128 strips in it. It had some other number. So there were some extras. So we had some things that weren't in the map. So this meant that every time we would run over an event, we would have maybe 20 or 30 calls to something that weren't in the map. So this is fine if you catch the exceptions, because if you look up something on the map and it's not there and you get an exception, you catch it, that's okay. But the problem there is that if you're trying to debug a program where another exception somewhere else in the program that you don't know where it is and you want to set a breakpoint on the exception, will get caught on these exceptions many, many times. So if you're tracking down a stubborn bug where an exception is thrown and you want to catch it, then all the thrown exceptions that are normal non-buggy features of the program will impede your ability to debug that. So that's why I put these checks in there explicitly rather than leaving them as exceptions, because they might not be exceptional. Other things that are slow, cloning TH1s I discovered a long time ago is really, really slow. That's because TH1s contain more than the histograms. They contain a lot of titles and pavers and things that aren't always relevant to what I was doing. So what we did for this was for some statistical limit calculator, and I was passing things around as TH1s. Essentially, we just not use the TH1s, we used plain old vectors of floats instead. But it took some coding to remove all the TH1s because we actually wanted to make plots sometimes and had to copy the vectors of floats back into a TH1 and make a plot. But the code was sped up by using less than all the baggage of a TH1 because cloning was so slow. Formatted IO can be super slow too, because there's a character string that has to be computed from a floating point number. So, or even printing out strings requires a lot of string manipulation and calls to the operating system to get the formatted IO to a file or to the screen. So you may find in a bunch of code MF that MF has the message facility log info, and usually we turn off the info print flag because there's a lot of debug information that most people aren't interested in looking at. And a lot of these MF log info calls still do all the string processing, and only after all the string processing is done do they look at the switch and say that I'm not supposed to print this out anyway. So you may end up with a whole bunch of debug output that slows down the program, even if it's not being output. If it is being output, it fills up disk and takes a lot of CPU as well. Some programs can in fact be dominated by formatted IO operations. One thing is error messages. If you've got an error message or throttling error message is sometimes a good idea. If you've got billions of the same error message, you get bored looking at it, and you may, if you're printing out your own error message, you might want to reduce the number of times it gets printed out. Okay, sparse matrix tools are good if you're using big matrices, and it's very easy to make a big matrix on DUNE because we have so many channels and so many ticks. And if things are sparse because only a few channels got hit and then only a few ticks have signal on them, use sparse matrix tools or regions of interest. Minimize database access operations. Those can be slow. They may not take a lot of CPU, but they sure take time because you have to do a network communication to some server somewhere, and you may even overload the server. So bundle the queries together. If you want a whole bunch of variables all at once, don't make a bunch of individual queries, collect them all together and query them all at once. You get a bulk discount with database operations usually. Standard vectors are interesting and fun. You should use that rather than the bad old days in Fortran. What we would do is we would allocate memory at the beginning of the program and define the size of arrays that we would use that would be big enough to process whatever the biggest problem that we anticipated the program to happen. So if you have an array of hits, you would have to declare it in Fortran to be at least as big as the biggest pile of hits you ever wanted to process. And if you ever saw more, then your program would fail. And if you were smart, you would put an error message on it. Those were the bad days. These days, you just allocate memory with standard vector, you push things back, and standard vector will grow to as big as it has to be, and it won't grow any more than it needs to, because every time you use it, then it gets to be the right size. The problem with growing a vector like this is that when you push something on a vector, it asks, do I have enough space at the end of the vector to push the next element? And if not, it will double the memory of the vector, and it will reallocate or allocate new memory and then copy the existing elements to the new place, because the vector has to be contiguous, has to find a place in memory that is big enough and contiguous to store the double size array. So there's a memory allocation, there's a copy, and then there's a deallocation whenever a vector grows in size by a factor of 2. So if you know in advance how big your vector is going to be, you can eliminate this copy and double and allocation by reserving the size of your vector before you push things back. And that way you'll eliminate the need to do the this allocation and copy over and over again. Okay, so those are some How much time do I have? Do I have?
So,
until
so
then?
you just reinvented Fortran.
Yes, right. In fact, a lot of C++
I'm looking at
features
the,
feel like
you
Fortran.
technically are, oh, I have to get onto the right thing. I think you are technically already out of time. But no, there's lunch. We're into lunch break at this point. No,
Oh,
maybe I'm wrong. No, I'm wrong. I'm just I'm reading it wrong. You still have 45 minutes in which
Yeah.
to ruin the lives of people. I will point out that clarity and reproducibility and not doing super tricky things is sometimes a good idea. You do not want to write code that is very fragile in order to save a very small amount of time.
of course. And there's a famous quote, I think it was Donald Knuth, who said that premature optimization is the root of all evil.
But Donald Knuth is a very clever man.
Right.
Given that he wrote LaTeX, well, Tech, which is still in use and more robust than anything else, almost 40 years after the book came out, I think. In fact, when you're using Tech, you are using code that was written 40 years ago. Old Donald knows how to write code.
Mm-hmm.
Oh, Donald knows how to make you write code.
So we've already talked a bit about optimizing memory by using containers that grow and shrink in size to match what your problem is. Sometimes it's good to use floats instead of doubles, for instance, because they take up half the space. And memory bugs and memory leaks can be tracked down using Valgrind. And maybe I should show you an example here.
Yeah, actually, could you show people how to run Valgrind? That would be very good. We've gotten some questions about that.
And how to interpret the results as well.
Yeah, why don't I go ahead and do that? So I've got this alias, which does essentially what the mission setup does, is it just sources the DUNE setup script and sets up the DUNE software. So this is my favorite thing to do. And I've got a Valgrind example. In fact, here was the missing run through that I did back in April of yesterday's exercises. So I did test it. They do work. Valgrind example. So that's my executable. I'm going to recompile that. So this is a little standalone program. It's not an art program because
how is sorry, I'm getting behind. So how have you set up Valgrind? How do you get Valgrind to be on DUNE 02? Is it set up automatically?
Yeah, when you set up DUNE software, which is what I did with my little alias.
Okay.
It sets up this version of DUNE software, and here's the dependency tree. David Adams, a while ago, added Valgrind as a dependency.
Okay.
But if you don't have it automatically, you can always set it up because there are versions that are installed.
Okay.
And use Valgrind.
Okay, I'm good.
And there it is. So what I'm going to do is I'm going to compile my program, and I've noticed that some people who run root don't always know how to run the compiler at the command line. So if you've got a little standalone program that doesn't use root, oh, you know what I'm going to, this program actually, well, okay, this will run at least partway. It's got a bug in it. And the bug is intentional. It's for instructional purposes. So why don't I go ahead and compile this program? Here's how you invoke the compiler. It's G++ is the C++ compiler we use by default. We also use Clang, but I don't set it up by default. If you don't set up DUNE software, you get the old SL7 G++ version from 2011, and the language has changed a bit. This particular program doesn't use any new language features. And then I'm going to memleak is the name of the source file, so I'm going to name the executable memleak also. and then I'm going to use the -G flag, which turns on the debug symbols. And let's see. So there's no optimization because I didn't turn on the -O. I turned on debug with -G, and I've said put the executable output in memleak and compile the memleak.c. So what does this program do? It illustrates a memory leak. So it loops over 10,000 instances of making a new array of integers. And this is something that people will get discouraged from doing these days. If you really want to declare variables, you should put them in scopes where when they go out of scope, they get deleted. So in this case, I've got a bunch of news that don't have corresponding deletes. So what this will do is this will allocate memory on the heap, not on the stack, and it'll leave it there as allocated. And only when the program exits is this memory going to get freed up. I've also got some other problems here. Note that this array of integers has 100 elements in it, but they're numbered from 0 to 99. If I set the 100th one, that's the first one off the end of the array. So this should be an invalid write to memory that I have not allocated. So that's a bug. And it might crash or it might not. So the behavior is undefined when I write off the end of an array. Here's another illustration of the same thing. Instead of this array, by the way, goes on the stack, and this array goes on the heap by allocating new memory on the heap. And I do the same thing. I write off the end of the array. And we'll see why I did this when we look at the Valgrind output. And here's something that's even worse. Here's a null pointer. This is a pointer to an int that I set to 0. So this tries to write the memory address at 0, fill it with 6, and that's going to cause problems. In fact, let's go run this program and see exactly what those problems are. So we get the fact that we got here, we printed out 5 and 6. So these off the end memory writes actually succeeded, and we printed them out, but we got a seg fault over here. Let's run Valgrind, because this program has a lot of very suspicious things in it. So I use -- leak check. And because it's not root, I don't have to turn off all the root noise. And then I just run the program. So Valgrind -leak check. Yes, memleak. And that will run Valgrind. And you'll notice that it, okay. So I got my output interspersed with the Valgrind output. And then I see that there's an invalid write of size 4 at line 20. So then I see 20. So Valgrind caught the second one, but not the first one. And if you look at the Valgrind documentation, you'll notice that, in fact, I've got it right up here. There it is. That the memory check says that Valgrind itself does some calculation of whether it thinks that memory is your memory or not your memory. And in this case, I think we just got lucky because the memory that was off the end of this array actually belonged to us, but as often as not, this may in fact cause a segmentation violation, segmentation fault. But this one, Valgrind did catch because it was on the heap, and we didn't own the memory after that, and then we got an invalid write warning from Valgrind. So if you're running Valgrind on a art or root program, you'll get a whole bunch of noise, but make sure you look for the invalid writes and invalid reads. And then the invalid read is on line 21. That's this printout statement. So we're looking at element 100 of an array that only goes up to 99, and that's an invalid read, and Valgrind will flag that as well. Then it's going to complain that we're trying to write to memory address 0, which is also invalid. Typically, memory or address 0 is write protected by the operating system, because that's a common mistake, is to forgetting to initialize pointers. So null pointers are sometimes useful, because then you should check to see if pointers are null, and that may be an indication to your program of that maybe the argument is missing, and then you have to do the right thing. But if you try to write to a null pointer, then you will get the segfault that we just got. So then Valgrind told us that, oh, it was this line, and it was an invalid right there. Then you get a heap summary from Valgrind as well. And then we find out that we have a memory leak. So we definitely lost about 40 megabytes of memory. And that comes from the fact that we've allocated all this memory and then we threw away the pointers to it. So we no longer have access to any of this memory or know where it is, because this J pointer goes out of scope after each iteration through this loop. We get a different pointer for J, and then we ignore it, leaving the memory allocated, but no way to access it. So Valgrind catches on that and says that we've definitely lost all that memory. So it's a good way to check for leaks with the leak check. Now, running a program in Valgrind is a lot slower than running it without, but you can usually save yourself a whole lot of time. There is no CPU limit on the GPVM, so you are encouraged to run Valgrind. Run just one event if you're running an art job with Valgrind. Limit the amount of data that's processed so that you don't have to wait forever. Often it takes like 30 times as long to run a job with Valgrind as without Valgrind. Okay, so what else? There is.
How would somebody run this on a, how would you do this if you had a debug, you would set up a debug build and you wanted to actually debug, say, a tuple creator or proto-DUNE Enna or something like that?
Well, invoking Valgrind is is the same with the standalone program as it is with an art program. So all you have to do is, my prog would be lar, and then you just give it the arguments that you normally give it.
Oh, okay, great.
Right. So you just have to put this little bit up in front.
And then you go to lunch.
And then you go to lunch or go to sleep.
Dinner and yeah.
Right. In fact, I think I'm going to do that for this afternoon when we, well, I might not run Valgrind, I'll run the debugger. In fact, maybe I should run the debugger on this because it's good to show. Although
yeah, that's a good idea.
I do have the what the heap check looks like. So memcheck looks for memory leaks and invalid reads and writes. If you have a program,
what is memcheck?
Yeah, we just ran memcheck.
Oh, okay, sorry.
And that caught the invalid reads and writes and told us that we had this leak. But the heap checker, sometimes things aren't bugs, but you still are interested in what's using all the memory in your program. So I ran Valgrind with Massif, which is the memory, the heap checker. So this is one thing that we didn't describe very well earlier here, is that there are two kinds of memory. There's the stack and the heap, and the stack contains arguments to methods and local variables, and the heap contains things that are allocated with new and delete. So the art event goes in the heap, and there are a whole bunch of other things that go in the heap as well. So Massif, which is some part of the Valgrind suite, here's my documentation, Valgrind, and table of contents, and the user manual will tell you how to run Massif. Massif. There it is, the heap profiler. So I recommend reading these instructions, especially because when you run the heap profiler, it's really just running Valgrind with tool equals Massif. Here's how you invoke it. And then it'll make an output file called massif.out. And we see that here. I got a massif.out, and it identified it with the process number to keep them separate. If you have a whole bunch of these in a row, you don't want them collaborating each other, so it puts a number on the end. So that file massif.out is not readable. You have to run this program called msprint on it, and that will produce this graph. And this graph is what we're showing here, that I ran an art job with Valgrind with Massif, and here's the command. I just ran Valgrind dash tool equals massif on this lar job. And I was doing this as a test to see where the memory was going. And you get a sample every now and then of how big the memory is. You get a snapshot. And some snapshots are more detailed than others. So the snapshots that have ampersands in them give you these tracebacks. And you get a list of the call stacks for all the places where the memory was allocated in order to debug what's been filling up your memory. And the colons here are snapshots that just have sizes. They don't have full tracebacks. The pound sign here are the high watermark. That's where the most memory was used. And I think you get a full dump on the high watermark, but I'm not too sure. So if you look through this, you should look to see what's, and sometimes these are a little bit tricky to interpret. So I was looking to see what was taking all the memory between versions of Larsoft. And this was an exercise I was doing about a year ago, because between versions of Larsoft, we had an extra ½ gigabyte for a job that didn't change what it was doing. And it was loading up all of these things. In this case, I guess it was TensorFlow, and there was some just-in-time compiler from Clang. Libraries were being loaded. And then I was comparing one version against another. But this is what a heap dump looks like. This can be useful. Maybe we should go back and look at the debugger. Let's debug this buggy program. So we compiled it with debug symbols turned on, and the debugger is not set up by default. I like the GUI debugger from ARM Forge Tools. So set up Forge Tools, and the debugger is called DDT. And DDT is very, very stupid in that it often can't find the program that you're trying to debug, because it doesn't look through your execution path. You actually have to give it a full path. Now, in this case, there's my program. It's sitting right there in my directory, so I can just DDT it. And then, because Fermilab is cheap, we didn't pay for apparently a support license. The debugger will still run. It's just that you can't bug ARM if you have a problem. So let's turn it on. And I haven't started it yet, but this is one reason why I like the GUI debugger, is because it gives me the source lines, and I can step one line at a time with this debugger. And I can inspect things. Incidentally, if you guys are on a Mac, you may find that you need a 3-button mouse. This one works with the right mouse button in VNC. And I can add this expression. I want to say, look at J. And I've got no J yet, but if I'm looping over it, I'll get a J. So here's a pointer on the heap to the new integers. And then I can also look and see how many I's I've gotten through. So I put an I in my expression list. And it will tell me what I is on every step. That's another reason why I like the GUI debugger, is because I can just keep on pressing the forward button, and then I can watch a little movie of what the values, how they change. So in this case, I should be able, and this debugger is actually pretty nice. It's got tooltips that tell you what some things are, might be suspicious. So this is reminding me that I'm allocating memory and that I'm not using it, and I'm dropping the pointer to it. If you click on the column to the left of a source line, you set a breakpoint. You can also set breakpoints with this little breakpoint menu over here with the right mouse click. You can add a breakpoint and put the line number on a particular source file line. This can be pretty useful, especially since, remember how art works, is that art is a very small program that loads up a whole bunch of shared libraries for plugins. So setting a breakpoint at the beginning of an art invocation usually means that the debugger doesn't know all the source code that you're going to debug because it hasn't loaded anything up yet. However, you can still set a breakpoint by listing the file that you want to set the breakpoint in and the line number. And even if that file and line number are unknown to the debugger when you fire up the program, it'll discover it when the shared object gets loaded, and then it'll load symbols, and then it'll set the right breakpoint. So breakpoints, when you set them, may not actually get set until the shared object library gets loaded, and then it'll put the breakpoint in. These are simple breakpoints because I only have one program with no shared libraries. So then I can keep on running until I hit the breakpoint. And I stop there, and then, oh, my I and my J went out of scope, so they're not there anymore. And then I can continue running. Incidentally, okay, so the seg fault that I just hit, this is the memory error which produced that seg fault error message, is not a catchable exception. So in C++, you can throw an exception and catch it. What throw will do is it will unwind the stack and go up the call chain until you find someone that is catching the exception. A seg fault is not like that. A seg fault is something that will terminate the program immediately, right where the seg fault happens. And I find these actually a lot easier to debug because you fire up the debugger and it will stop on exactly the line where the seg fault happened. And it's always a good idea not to run after a seg fault. And then they'll tell you, oh, this line caused the seg fault. I tried to write a 6 into memory location 0, which is really super bad. I think that's all I had for this debugger.
Okay, so just so people get this one, it's set up already, or we have to do, what do we have to do to get this debugger?
It's installed. You just have to set up Forge tools.
Ah, okay, so
Yes.
okay, let me
I think that might be in the instruction.
yeah, just making certain that people, I'm sorry if I'm asking, I'm not always following the instructions. Just making certain that people know how to do this, because one of the things is we see all this wizardry and then we can't reproduce it 15 seconds later.
Yeah, I think I might have it in this one. Yeah, I've got it in the afternoon session where we actually debug the program that we're writing.
Okay, good.
I don't have it in this session. I've got it in the next session. Okay. Very good. So
you're just saying that my method of just putting assert in every suspect line of code is probably not optimal.
Yeah, so sometimes you have to use cruder methods of debugging. The debugger is really great, especially with seg faults, because it'll stop and tell you exactly what the problem is. But sometimes the problem is a little more subtle and your program actually finishes and just gives you the wrong answer. And then you want to know, well, where is it that it's going wrong? And if you're processing millions of things and adding them all up, and one of those things out of the million is buggy, it's hard to set a breakpoint on that and identify what the problem is. You may actually have to put a little statement in there that prints things out when the bug happens. And sometimes if you've got a print statement that gets executed a million times and then the program crashes for some reason, it's still okay to print out a million things if only the last one is the one that you're interested in. But you have to print them all out because you don't know which one is going to cause the problem until you get to the problem. So sometimes a print statement's actually more effective than the debugger.
One comment being that, yes, if you do this kind of debugging, that's great, but please don't leave it in production code, because many of our jobs, we process 8 GB files. And it is certainly not quite frequently that we see jobs that have log files that are larger than the original, the 8 gig file they're trying to process. And this will fill the disk on your batch job. Your batch job may be failing because you wrote too much stuff out to the log.
I saw a user write out 200 gigabytes of error messages once. To
Yes,
delete the
don't
file.
be that person, because that person is going to be very sad.
Right. And regarding assertions, I think there's something in the build system that turns off of assertions in the prof build, but leaves them enabled in the debug build. And I ran into this problem just a couple of weeks ago because I was trying to debug something and I was using the debug build and it was crashing and I didn't know why. And it turns out that there was an assertion there that the assertion was buggy. So the program was fine. It's just that the assertion was asserting the wrong thing. It was asserting the inverse of what we wanted to assert. So it was always crashing on the assertion. And no one noticed this because they only looked at the prof test. They didn't test the debug. So that cost me an afternoon.
But you enjoyed it.
So much fun. Okay, so as Ken always tells you, use XRoot to stream your data in. That helps optimize I/O. One thing that I discovered a long time ago, back in the PAW days, is that if you use, say, separate method to calculate each histogram and spin over your T-tree once for every histogram that you make, you're actually much better off making all your histograms on one spin through the T-tree rather than spinning through the T-tree once per plot. So if you write a macro that fills in 10 histograms, it'll be 10 times less I/O to call that macro once than to call 10 macros, each one that fills in one histogram, and each one has to spin over the same T-tree. You can also read in only some T branches or leaves and not others. Root will do this by default, although if you run make class will give you a boilerplate macro with all the T branch declarations, and it will read in every branch for every event by default, and then you have to turn them off if you want your program to do less I/O. And often I/O is a lot slower than the CPU. Compression is always good. Even though compression takes CPU, often the disk can be slower than your CPU, and you're better off compressing and saving less data because you'll save time just because the disk is slower. Okay. I noticed a while ago that big programs take forever to compile. If you put all your methods in one source file, then G++, especially when you turn on optimization, does a whole bunch of source code analysis and is very slow. If you break it up, then the compile will run much faster. I think we have a hand up from Jake.
Yeah, hey Tom, we have a question in the chat from Wei Shi. Says, are you going to talk about how to check stack memory usage? The Valgrind Massif only look at heap memory.
Well, the stack usually is smaller, and I've seen the stack actually run out. You might get an error when you run out of stack memory. Massif has some options. When I was looking at the problem with the root and Larsoft version that was giving more memory, Massif originally didn't catch it. That's why I had so many tries through that. And there are switches to Massif called interpret pages as heap. And I think there might even be some way to include stacks. So is this Massif? Let's look at stack. Yeah. Snapshot details. Massif actually gives you stack size. So yeah, you might have to switch it on with this stacks equals yes. That's
Yeah. I mean, DUNE has a special problem, which is that our events are, well, our objects, memory objects are huge. And so almost anything you can do can get you into trouble rather rapidly.
Yeah.
I just put in I think I put it in the chat. There's some instructions if you want to be running these things on a local machine, so you don't have to worry about doing it over the network to a GPVM. There is a way of getting the CVMFS mounted on your local Unix machine and being able to basically run a complete DUNE setup from your local Unix machine. You have to be friends with the system admin, which I am. But this is something people can think of as an option if you are worried about not getting enough things not working so great on the remote machines.
Yeah, especially the GPVMs are shared by 1,300 DUNE collaborators, and not all of them are very careful about what they're doing. You may notice that the load averages on these GPVMs are sky high. Sometimes they're like 20 or more because people are doing dumb things like editing things in Vcache with the text editor. So having your own local machine is great.
Yeah, there's a couple of GPVMs that have been pegged for 2 months at this point.
Yeah.
Somebody did something that made them very unhappy and nobody ever caught it.
Well,
Oh,
it's
well.
not actually using CPU. The load average is a list of all the processes that are stuck as well as those that are running. So the machines are still usable. It's just not nice to have all these stuck things. And that's mostly Dcache. It's people running VI on a file in Dcache scratch. And the file went immutable because that's what Dcache does. And then VI gets stuck in the D state and you can't even kill it. And that adds 1 unit to the load and it doesn't do anything, but it confuses the load average plot.
Yeah, unfortunately, we don't have the power to reboot these machines or kill individual processes. So
actually, we do. I have the ability to.
You do? Oh,
yes.
Maybe I wouldn't let me have that power.
But some of these IO stuck processes can't be killed anyway. You actually have to reboot the machine, and I can't reboot the machines. But if I put in a service desk ticket, then let's see, Ed Simmons goes out and reboots the machine.
Okay.
He's very friendly about it. Usually when
Worth a try.
Yeah, he gets to it right away. So what else do I have? Oops, I want to go back here. So minimizing, yeah. Minimize includes workflows. You can read all these things. How much time do I have left? Oh, I got half an hour, don't I?
Yeah, we can look at the pictures.
Yeah, because there are other things that can speed up your life.
Someone asked, what is ARM DDT? Is that in the notes or is that this afternoon's notes?
Yeah, it's in the afternoon notes.
Okay, yeah,
So
I will. You've gotten ahead of yourself, Tom.
I got ahead.
So maybe we should just make people ask questions.
Yeah.
Okay, so since I'm a brutal professor, I suggest that everybody put their most burning questions. Somebody has asked, yeah, everybody put your most burning question in the chat for now.
Yeah.
And then Tom will read the chat and answer your questions. This is your chance to talk to the guru. Normally you have to climb to the top of the high rise on your knees in order to talk to this guru.
So also, please feel free just to jump in and say something. I don't mind being interrupted. Okay. I've also noticed that having your own computer with storage is very useful. So one of the issues is that the app disk fills up and the data disks sometimes are slow and they fill up. So having your own 1 terabyte or more local disk on your own desktop is so nice if you're doing an analysis and don't want to get clobbered by other people. Okay, just reading the chat since I'm supposed to. Floats versus doubles. Yeah, there's quick, but they take more memory. Or doubles take more memory. In general, if you're not worried about memory because you're doing a small problem, just use double for everything. And literal constants in your code, like 3.0, if you put that in your code, gets interpreted as a double. Does this work with root? Of course.
Yeah, well, my question is, I find that debugging, I build my own root executables to just run scripts, and I don't know what compile flags to put in so that I don't just get this complete dump of junk at the end.
So
It doesn't give me the line number. It doesn't give me squat. It just says I segfaulted. I'm sorry.
yeah, so I never debug an interactive root session this way, especially because it's running a C interpreter, C++ interpreter rather than a compiler.
Yeah, no, I compile my code.
Yeah.
My code is compiled, but let's see. Maybe I'll try Valgrind on it sometime. But
It turns out that you can build your root code without using the root environment by linking with the root libraries. And the script is called root config. Root config.
yeah, okay, yeah.
And if I run root config --libs, it'll give me a whole bunch of things that I can put on the command line. So if I want to compile a program like, there it is, and I want to link with the root config libraries, root config libs. What this will do is this will put all of those things that root config --libs spits out on this command line. That's what the backtick means. Back quote on the bash line means take whatever's between the back quote, execute it, and whatever string it puts out, interpret it as if that were typed in on this line. So that will put all these little -Ls for linkage to root libraries on this line. So that will compile the program and link with root libraries. And I think that there are other options. I think you might even have to say minwi separately or something.
Yeah, no, I'm using CMake, and I don't think I'm doing this because I got the includes. I'm doing a real compile, but I don't see the root config in my CMake. So, oh well.
So CMake stuff, I think we've got a lot of the root libraries defined with like root basic lib list is something that the set build tools provides for us. So we're not even using root config. We have our own list.
Yeah, I'm using this raw actually for testing Minerva analysis. That's why I just was wondering if there was a way around this. This is somebody who builds their own root stuff. Okay, anyways, that was just,
yeah.
I will figure out what I'm doing wrong.
Yeah, when I debug something, I prefer to have a separate executable. So art is fine. Interactive root, I've never debugged the interactive root.
No, this is not interactive root. This is a separate executable. I must not be building it right. Okay, I'm doing, link directories, root library _dir, but probably not putting in the right flags. Okay.
Okay.
So.
More questions in the chat? Will it slow down the node? The answer is not any more than just running up any other program. So Valgrind is just a user mode program like any other program. Sometimes it can take memory though. And the interactive GPVM nodes have, I believe, 12 gig for 10 through 15, DUNE GPVM 10 through 15, and only 8 gig for DUNE GPVM 1 through 9. So running Valgrind will use more memory than not running Valgrind. And the system has this process called the killer, the out of memory killer. In fact, we will notice that when we get to the compile your code part later this afternoon, is that if the machine runs out of memory, then it starts killing processes. And ideally, the killer is smart enough to kill your process if you're the one who is hogging the memory, and it usually gets it right. But if you're hogging a bunch of memory and it kills someone else's process because the node's running out of memory, then someone else may get mad at you because you stepped on their work. Furthermore, the killer isn't very smart, and sometimes the node will just lock up. So it's usually just memory. CPU is not a big deal on the GPVMs. Most of our code is single threaded and Valgrind doesn't create more threads. So you'll just be taking one CPU out of 4. If you run more than 4 simultaneous processes on a GPVM, yes, you will slow it down. But if you
Yeah,
run
generally do not do this.
less than 4,
Never run more than 4 or even come close to it on the GPVMs.
Right.
It's like walking into a room with a plate of cookies and eating all the cookies.
If you want to know how many CPUs are available on a GPVM or any other node, you can look at /proc/CPU info, and it will list each one out. And starting with 0, so 3, processor 3 is actually the 4th processor because everyone counts from 0, right? Another fun utility is called HTOP, and this will list CPU busyness by each CPU, and you'll get user mode and system mode is green and red respectively, and a nice representation of how much memory is being used. The actual list of processes here isn't as useful as the ordinary top command. Top command here will sort by CPU usage. 100% means using 1 out of the 4 CPUs on this. You note that the load
You said
average.
it was, okay, so just one thing just for, oh, okay, this is great.
Yeah.
I like HTOP. What was the other one? /proc/what?
CPU info. And that's just a listing what's available on the machine.
I'm saying proc/CPU. I may have to do a KX509. It's saying it says permission denied.
Oh, it's in /proc/CPU info. Can't just
Yeah.
check that?
Oh, it's cat. Oh, okay. I thought
Yeah.
it was an executable.
It's not an executable, it's just a file.
Okay.
So this says that these CPUs are really old. They're Broadwells. They're newer than what's on my laptop, which is Haswell, but this is like 2015 vintage CPU, 4 cores. And I sometimes just get the memory from top. This will tell you how much memory is. So this node is one of the, it's DUNE GPM 13. It's got the 12 gigs of RAM, and you can see that it's not terribly full at the moment. Half the swap is being used. I'm not so sure I understand why the swap is so small. It's only got 2 gigs of swap. I think they want to discourage us from filling up the memory. So if someone has a memory hungry application, they don't want it to swap to disk, they'd rather just kill it. Okay. Am I missing some of these questions? So we have the stack, so work with root, HTOP. Yeah, I use top. It'll give the memory and the CPU. And I think that there are ways, let's see, if I press question mark, it'll tell you what letters you can type individual characters, and that will change the sort order of the display. So normally top displays by top CPU, but I think you can toggle it to sort by top memory usage. And I normally look at the resident memory size to see how much memory it's using. Okay, and what else do we have in the chat? If you spend an afternoon or even days on debugging, it's normal. Bugs are hard to find, absolutely. In fact, I've found that debugging is kind of like going through the stages of grief because you have to believe that there is a bug, and you have to accept that you've made a bug, and then once you find the bug, you actually have to fix it. And finding someone else's bug is getting very common because we were living in a large collaboration. We end up finding other people's bugs, and then convincing them that they have a bug is an interesting.
Oh God, no. There's one thing about bugs is that, you know, if you're going to divide by a number, okay, especially if you're using integers, for example, what are there? There are like 4 billion 32-bit integers.
Yeah.
There are almost certainly a single DUNE event. No, it's not a single DUNE event, but a single file of data from DUNE has 8 gigs. So, and a lot of it is going to be like random shorts from the readout. The odds are that you will sooner or later hit almost any possible combination of bits in code. So just assume that whatever you're doing, you're going to hit that special value that causes your code to crash.
Mm-hmm. In fact, here's a cute little command. Speaking of arbitrary bit strings, it's the strings command. And what this will do is it'll find all the printable strings that I believe are 4 characters long or more. So if I want to see what the compiler put into this executable program, I'll get a list of all the error messages it can possibly emit, as well as symbol names and debugging information and other things in that. You can do this on a root file too. And remember, config dumper and friends print out strings that have been encoded in the root file for the configuration of the job. You can just use strings and it'll do the same. It'll print out all the printable things and you'll find all the fickle configuration in there too. And as per Heidi's comment, you'll notice that all of the unprintable things, sometimes just those random bit patterns from all those shorts will make printable characters, and then you'll get, that's what these things, some of these things are just random characters that got interpreted as character strings. So if you have a big enough file, you'll eventually hit any bit pattern that you desire. This affected the root distribution a few years back, or maybe just last year, because the antivirus checkers were flagging some root executables and shared libraries as having viruses just because they had bit patterns that corresponded to the signatures that they were looking for viruses. Even though the virus was not present, it was falsely identified as having a virus.
One could wax philosophical and point out there's a hell of a lot of leftover virus DNA in your DNA. So
right. And there's a lot of crap code in DUNE's GitHub repository for the same reason. But people just haven't been deleting it. I tried cleaning
well, it
up.
turns out some of that crap DNA is structural, you know.
Right.
It actually tells it how to fold.
Right. Okay, so other general advice, some things, this was also in the chat, is that sometimes if you tweak your code to be fast and efficient with memory, it can be very hard to read and it can be very hard to maintain. So people time is valuable too, and it has different units than computer time. We pay a lot for people time, so be gentle and friendly with your people who are going to take over your code. And no one maintains code forever. It is always checked into a repository and always given to someone else to maintain. If you are a grad student, expect your code to be given to the next graduate student. In fact, you will usually be the person to train the next graduate student to use your code. And so someone else will maintain it. So code in a way that makes that handoff process easy. And that means things like update the comments when your code changes. You change your mind about what the code does, change the comment too, not just the code. Update the names. So if you change your mind about what you're calculating, give it a different name instead of just reusing the same variable. Const is a good way to protect yourself from overwriting things. In fact, speaking of overwrites, a less used, but sometimes if you're really frustrated, feature of the debugger is called watch points. And I don't know, let's see, I got 15 minutes left. Do I want to set a watch point? People want to watch a watch point? I haven't set a watch point in a long time, and I haven't practiced it in years. So what a watch point does is it looks for changes to memory locations. And maybe I can do that. You want to watch me watch a watch point? Set a watch point.
But you just have to make your mem code do something, change a memory location, right? Like
Right.
P of 10 to 100.
Let's do that. Okay,
And this is in Valgrind or in this other program?
we're going to do this in the debugger. Let's comment out
Oh, the
the,
debugger.
let's
Okay.
comment out the bug so it doesn't crash. And let's compile it. Let's not link it with the root library because I don't have to. And let's run it. So that's nice. And then, so actually, let's see. I'm wondering if I can create an example where something is unexpected. But let's try it. I will just show what a watch point looks like. And it's not going to remind me that I don't have a support contract twice. Now, I don't actually have P defined until I actually execute that line. I still have my breakpoint. So if I click on the breakpoint, it'll go away. You can also disable a breakpoint. So I've got this breakpoint. If I've got this, I think I can right click and I can disable it, meaning that it's still there in case I want it back, but it won't break on it. And it'll just remember it in case I want to re-enable it. And then I continue on. So now I have my P of 100 array. And now I can set a watch point, watch points. Let's turn this on, add watch point. And let's see, P of 10, I can watch P of 10. And I think I can actually watch a whole range. And you should look at the documentation because maybe watching the entire array of P. So what this will do is on every instruction that the program executes, it will go and execute routines in GDB, which will compare the contents of this memory location that I'm watching. And if they change, it'll break and show where the change happened. So here we stopped a watch point on P of 10, and it'll tell me that the old value is 0 and the new value is 100. So one of the reasons why you might want to set a watch point is because you have a memory overwrite. And in this case, I've got a write off the end of one array. And you may discover that if you didn't have a segfault, that this memory that you scribbled off the end actually belongs to a different array. And that you put a value into a different array unintentionally, and you have no clue why that happened because this was in a different part of the program and it just happened to be next to it in memory where this array ended up. So sometimes I've been very frustrated as to say, well, why did the value of this thing change when I didn't do anything? And then I set a watch point in the debugger and found that this other place far away in some other part of my program was inadvertently scribbling on some memory that it didn't intend to, and it changed something that that was hard to figure out where the bad value was coming from. So if you've got a variable or an array element that is getting some screwy value, and by the way, one indication of screwy values that get inadvertently put in there is that if the method that is inadvertently putting the data in there tries to put something in of a different type. So if it tries to write a floating point number into memory that gets interpreted as an int somewhere else, you'll get a crazy value. You'll get numbers like 3 billion when you might expect a number like 2. And putting ints into floating point numbers is even more spectacular. You get numbers like 10 to the 100 as floating point numbers. In fact, I've seen places where I think it was Genie doing tau decays. There were something like momentum was coming out 10 to the 100. And people were complaining that the energy and momentum was not conserved and the whole universe was imploding because of this particle that Genie made with 10 to the 100 GeV in it. It was just a memory overwrite or uninitialized memory. What do I talk about uninitialized memory? I should talk about uninitialized memory. Yeah, I do talk about uninitialized variables. So always initialize variables when you declare them. And do I do that here? So here, when I declare the J pointer, I actually fill it with something. Here I've declared an array, but I don't fill it with anything. If I have an int k equals 5, for instance, it's always a good idea to put an initializer. You have two ways of doing this. You can also do that to initialize a variable. So it's preferable to do that to just leaving it uninitialized. And the problem with uninitialized memory is that k gets pushed on the stack, and whatever was put in the stack before is what k is. So in fact, if I do standard, okay, this has a large chance of being 0, but it's actually undefined. So the value of k is whatever was on the stack when it was allocated and it wasn't cleared out. Back in the old days, VAX Fortran had an option called demand 0, so that when you allocated new memory, it would be cleared out to be 0. Whoops, I don't really want to run it in the debugger. Let's get out of that and let's just run the program. I want to see what k is. But k ended up being 0, but it could have been anything. And it could be a number like 10 to the 50 or something like that. So the demand 0 option for VAX programs actually took time, because every time you allocate memory and fill it up with 0, that takes CPU and memory access. So the standard C and C++ tools don't do that by default. They expect you to do it if you really want that. So if you want your memory to be 0 when you allocate it, you have to say that and do that, or fill it with your favorite variable, because it's not done for you. And you might get a random non-reproducible answer if you don't initialize.
And the debug builds of DUNE software. So if you're writing stuff within DUNE software suite, the debug builds will throw an error from the warning of the uninitialized value. And then we'll hunt you down and ask you to, well, we'll probably change it, and then we'll ask you to keep doing not that in the future.
Right. So let's turn on the warnings. So you'll notice, oh, I've got my unused variable, and also k is maybe uninitialized when used. So I'm reading this uninitialized variable when I print it out. And our build system actually treats warnings as errors. There's a flag for GCC which will take all these warnings and treat them as errors, which will stop the build process. So that means you have to clean up all your warnings when you're compiling DUNE code, not when you're compiling your own code. Minimizing the scope of variables is useful as well. So if you are looping over something and you declare a variable to contain the value of something that is only meaningful inside the loop, make sure you declare that variable inside the loop. So if you're looping over hits and you want the X position of a hit, declare X as a variable inside the loop, and then it'll go out of scope when the loop ends. If the variable is declared outside the loop and it still exists outside the loop, you might be tempted to use it. And then it will have the contents of the last thing that the loop had. So you might get the X of the last hit. Maybe that was looked at in the loop. Maybe you want that, but usually you don't. So if something is local to the loop, make sure you declare it inside the loop. You can do this even without a loop. You can put braces, you can put random blocks inside your program. You can actually limit the scope. I can just put a brace like this here without a for or an if or anything like that. I can just lock all of these things up in a brace. And what this will do is this will make everything inside that's declared go out of scope, and these variables will disappear and they will be unavailable later on in the program. So this is kind of useful if you're just cutting and pasting a whole bunch of someone else's code into yours, and you don't want the names to collide. You can just limit the scope within a method by just putting braces around it. Okay. And I think I'm just about out of time. We do have some presentations from Kyle on thread safety. Thread safety is an interesting issue, mostly because of memory. So we've got lots of cores in our CPUs, and it sure would be nice to use them all while we're running a job. The current model from ART is to load up more events and process the events or trigger records simultaneously, but our trigger records are big, so that actually doesn't save us RAM. You might as well run a separate job, single-threaded on each core. However, there is a lot of shared stuff, so the code and the geometry description, shared libraries do take up space, and it would be nice to use only one copy of that in memory and then make all the cores process the different data memory. So that's the idea behind multi-threading, but you don't want the threads to write over memory that's used by another thread that's expecting the memory to be local to that other thread. So that's the main challenge in writing multi-threaded code, is to make sure that the memory that is in use by one thread is not overwritten by another thread unintentionally. So one way to protect against that is to make things const, so that they can't be overwritten. Another thing is to split off memory that is specific to a thread as a separate memory. And another thing is to have, say, gatekeepers that schedule changes to the memory. So I think if you put things into the ART event, then those are scheduled in a way so that you don't have clashes between threads. So there's a nice presentation from Kyle describing all of these things. So in general, say modules are easier to keep multi-threaded, but services are tough because they're shared by all the modules in an ART job. So a service, because it's a singleton, there's only one instance of a service, and it may be called by a whole bunch of modules in different threads. And if the service has any internal state, like the last file that was read or some variable it keeps internally to it, it might end up confusing one thread when another thread modifies the state of a service. So stateless services, things that just return values like the drift velocity, are easy to make multi-threaded because you just have one copy of the information, it just distributes it. But if the service actually collects information and stores it, then that can be hard to make multi-threaded. Okay. Oh, and on workflow optimization, write your favorite data as tuples or trees, and then make your histograms and decorate them separately. So I found that when making plots for a paper or presentation, I have to tweak the labels and colors and line thicknesses and the dashes and the legends and the titles incessantly in order to make them look good. So if you write out your histogram, sometimes making the histogram takes a while because you have to spin over a T-tree, or even worse, run an ART job. And you don't want to redo that every time you change the bold font on your axis title, or how many log labels there are. So write out your histograms to root files and then decorate them in a separate script. And so general advice to speed up your life. Okay. Is the session until noon?
It is till noon, and it is noon, so everybody gets to go away for 30 minutes to have lunch. And then you come back and instill more wisdom.
Okay.
So I learned a lot. I don't know about these guys, but
Might be more.
I just put in print statements and use asserts. That's me. It's worked since 1972. It still works.
Yeah.
Here it is.
Yeah. Okay. So we've got another session.
Another session from hell. So thanks. I don't know about anybody else, but I'm learning a lot. We just need to make certain we capture all these gems of wisdom that you're throwing at us, that they're actually in the thing. Okay, let me see. So we've got people going. Let's see, we are, I guess, moving on to the, let me look at this. Okay, so here we are. Where are we at? We are at expert in the room, and you were going to show us how to modify a module in Larsoft.
Yeah.
And then there's going to be a quiz on programming practice.